Uh, okay, so let's get started. So today we're very happy to have Ashvin Swaminathan, who will tell us about composition of binary quadratic forms. So take it away.
All right, thanks, Simon, for the introduction and for the kind invitation to speak. Today I want to tell you about binary quadratic forms, which are beautiful mathematical objects that have been under study for many millennia now, and they motivated much of modern number theory. So I want to tell you about them. So let me start by defining this. So definition, a binary quadratic form over the integers z, which I will henceforth abbreviate by BQF, is a homogeneous polynomial f in two variables, which I'll usually denote by x and y, of degree 2 with integer coefficients. So what does a typical binary quadratic form look like? We denote it by f, sometimes also write f of x comma y, and it'll look like a polynomial of the form ax squared plus bxy plus cy squared, where a, b, and c are integers. Okay. So that's a binary quadratic form. And it is also convenient to think of this form in terms of matrices. So we can actually factor this polynomial using matrices. And we can do that as follows. So this is just the row matrix xy times a, b over 2, b over 2c times the column matrix xy. This is an interesting factorization of the polynomial in terms of matrices, and this will be useful in what follows. And I should mention that if you have any questions at any time, probably not going to be able to look at the chat, but please just feel free to interrupt. And yeah, so that's what a binary quadratic form is. Sometimes in what follows, just for the sake of brevity, I'll denote this binary quadratic form f with coefficients a, b, and c by just the triple of integers a, b, c, because that determines the binary quadratic form. Okay, so that's the definition of a BQF. Now, given f a BQF, we can think of it as a function. I'll denote this function by phi f. It's a function on pairs of integers with values in the integers. And this function simply takes a pair of integers, x, y, and it produces the integer f of x comma y. We can associate this function to a BQF. And the fundamental question that has been under study for millennia now is, what does the image of the function phi f look like? Okay, so that's a bit of an ambiguous question. So let me make it precise. So specifically, one question we may be interested in is which integers are represented by f. So when I say an integer represented by f, what I mean is which integers lie in the image of the function phi f. So yeah, so represented by f just means line the image of phi f.
There's
So another way to say that.
There's a question in the what is a homogeneous polynomial?
Yeah, so a homogeneous polynomial is a polynomial where every term of the polynomial has the same degree. So as you can see in this binary quadratic form f, every term has degree 2 in the variables x and y. Yeah, so that's the definition of homogeneous. Yeah, so the first question we'll be interested in is which integers are represented by a BQF. Another way to say that is for which integers n do there exist integers x and y in Z such that n is equal to f of x comma y. That's another way to say that same question. Okay, so that's the first question we'll be interested in. And another question we will be interested in is which binary quadratic forms represent the same integers as f. So if you fix a binary quadratic form f, you can ask which other BQFs represent the exact same integers that f does. Okay. So in this talk, I want to start by giving a partial answer to question number 2. Okay. And in order to give that answer, I need to make a definition. So definition, let f and g be BQFs. Okay. Then we'll say that g is related to f if there exist integers s, t, u, and v such that the absolute value of sv minus tu equals 1, and such that g of x comma y is related to f of x comma y in the following precise way. So g of x comma y is just f of sx plus uy comma tx plus vy. So g is related to f if you can get g from f by doing a linear change of variables, where the linear change of variables is to replace x by sx plus uy and to replace y by tx plus vy. And this definition is much easier to state in terms of the matrix factorization. So let me do that. So that is to say, if we write f of x comma y as x, y times a b over 2 b over 2c times x, y, and if we let m, is there a question? Yes, not? Okay. If we let M be the matrix S, U, T, V, then G is related to F by the matrix M if G of X, Y equals X, Y times M transpose A, B over 2, B over 2C, M times X, Y. So the effect of this matrix M is to just take the matrix here that defines the BQF F, and then to multiply that matrix on the left by M transpose, on the right by M. and that'll give you the matrix corresponding to G. So that's the notion of G being related to F. So given that notion, we have the following little result. Lemma. If G is related to F, then F is related to G. Okay. In this case, we say F and G are equivalent, and we write F tilde G to indicate that they're equivalent. Okay. So let's prove this. So let S, T, U, and V be the integers as above in the above definition. Then f of x comma y is equal to this matrix factorization. And then we can just sort of multiply by 1 in 2 different ways. So this is equal to the column vector, or sorry, the row vector xy times m transpose inverse m transpose times a b over 2 c times m inverse times xy. And then associativity gives us that this is just xy times m inverse transpose times m transpose a b over 2 c times m times m inverse xy. Okay, so now you might recognize this here as being the matrix corresponding to G, so that's good. And now we can calculate.
There's a question in the chat. Can you tell what mt and m to the minus 1 are?
Yeah, so m was the matrix SUTV. So m transpose is going to be the matrix STUV. That's just the transpose reflection across the main diagonal of the matrix. And I'll tell you what m inverse is now. So m inverse is going to be plus or minus v minus u minus ts. So m inverse is the matrix with the property that m times m inverse is equal to the identity matrix. And you can check that this matrix I've written down in red will have that property. Okay, so the point is that we know what m inverse is, so we can write m inverse xy as plus or minus vx minus uy and minus tx plus sy. Okay, so using this relation and combining it with this formula here, we get that f of x comma y is equal to g of vx minus uy and minus tx plus sy. And so that's exactly the condition for g to be, or f to be related to g. And so in fact, f is equivalent to g. Okay, that completes the proof. Okay, now on to the next little result. So lemma, if f is equivalent to g, then the image of phi f is equal to the image phi g. Okay. So again, let S, U, T, and V be as above. If g of x comma y is equal to n, right? So if g represents the number n, then f of sx plus uy comma tx plus vy, well, that's just g of xy. And so that's also equal to n. So if g represents n using the numbers x and y, then f will represent n using the numbers sx plus uy and tx plus vy. Okay, so if g represents n, then f represents n. And you can just do the same argument in reverse. So if f of xy equals n, then g of vx minus uy comma minus tx plus sy, well, that was just f of xy, and that's n. So f and g represent the same numbers. So equivalent BQFs represent the same numbers. And well, so that means that equivalence is kind of an interesting notion with respect to the questions that I posed earlier. So now what we want to understand is the following question. How could we detect if two BQFs, F and G, are equivalent? Okay. So to answer that, you need to make a definition. The discriminant of a BQF okay, so there's a question in the chat about when was this notion of equivalence figured out? I have no idea. I would imagine it was known to very ancient types. Okay. Yeah, so if we have a BQF, f of xy equals ax squared plus bxy plus cy squared, the discriminant is denoted by delta of f. And this is just b squared minus 4ac. That might be a very familiar quantity to all of you. That's just minus of the determinant of the matrix associated to f. Okay, so that's the notion of discriminant. And regarding the discriminant, we have the following little results. So if f is equivalent to g, then the discriminant of f equals the discriminant of g. So the discriminant is invariant under equivalence of BQFs. That's what we say. So let's prove that. Okay, so let M be the matrix as above, relating G to F. Then the discriminant of F is minus the determinant of A, B over 2, B over 2C. And now this is just equal to minus, minus the determinant of M transpose times the determinant of A, B over 2, B over 2C times the determinant of M. And the reason we can do this, multiplying by the determinant of M transpose and the determinant of M, the reason we can do that is that the determinant of M equals the determinant of M transpose. And in fact, if you take their absolute values, they're equal to 1. So that's why we can multiply by those factors. That doesn't change anything. And now by the multiplicativity of the determinant, this is just minus the determinant of M transpose A, B over 2, B over 2C M. And now you might recognize this product of three matrices as being the matrix corresponding to G. And so by the definition of discriminant, this is equal to the discriminant of G. So the discriminant is invariant under equivalence of BQFs. Oh, yeah. Okay, I can't do basic math anymore. So yeah, so you have to multiply that by 4. There's a missing 4. And, oh, goodness. Okay, there we go. Yeah, sorry. Okay. All right, so the discriminant is invariant under equivalence. Now you might ask, well, what other polynomials are invariant under equivalence? Oh, so there's a question. Why was the -4 chosen? Does it simplify the formula? Well, I mean, you can kind of, just for the purpose of invariant theory, if you're just looking at polynomials invariant under equivalence, you don't really need to care about scalar factors. But there's some number theoretic reasons why you would want this normalization where we multiply by -4. For example, so I'll just state this as an aside. So if f of xy is a BQF, then f has a repeated root modulo p if and only if p divides the discriminant, b squared minus 4ac. Now, if you were to scale b squared minus 4ac by other numbers, that property won't be true anymore. But yeah, so there's some number theoretic reasons why we normalize it this way, but for the purpose of invariant theory, just understanding which polynomials are invariant, you don't need this normalization. Okay, that's a little bit of an aside. But given that the discriminant is invariant, you could ask, well, what other polynomials in the coefficients of a BQF are invariant? We know b squared minus 4ac is invariant. And so any polynomial generated by b squared minus 4ac will be invariant. So any polynomial of the form c naught plus c1 b squared minus 4ac plus c2 b squared minus 4ac squared all the way up to, say, ck b squared minus 4ac to the k, where the ci's are integers. That's also going to be invariant under equivalence. Okay. So I'm going to call this polynomial here star, because I'll use it later. And now we have the following very beautiful theorem, which is stated as follows. So let D be a polynomial on the coefficients of a BQF, some polynomial in A, B, and C. And suppose that it is invariant under equivalence of BQFs. Then D is of the form star. So in the literature, this theorem is stated as follows. The discriminant is the unique polynomial invariant of equivalence. That's not quite accurate because you can take the discriminant and look at any polynomial of the form star, and that's also going to be equivalent. But basically, the point is that the discriminant is the only real invariant, and then every other invariant is generated by it in some polynomial way. Okay, this is our first kind of big result today. Let's prove it. Okay, so to prove it, I'm going to start by working modulo b squared minus 4ac. So what does that mean? Well, when you work modulo a number n, you just set n equal to 0 everywhere. So working modulo b squared minus 4ac means whenever we see an instance of b squared, anytime we see b squared, we just replace it relentlessly with 4ac. And so then we can write the polynomial DABC as in the following form. D0 of AC times b to the 0th power, that's equal to 1, of course, plus D1 of AC times b to the 1st power. And the reason we can do this is that we're working modulo b squared minus 4ac. Anytime we see a b squared, we're setting it equal to 4ac. So the only powers of b that can show up are b to the 0 and b to the 1. And then the coefficients of those powers have to be polynomials in a and c. And so those are d0 of ac and d1 of ac. So this is all true mod b squared minus 4ac. Okay. Now we have a little intermediate claim. First claim is that d1 of AC is equal to 0. Okay, so let's prove the claim. And when I say equal to 0, I mean honestly equal to 0, not just equal to 0 mod b squared minus 4ac. Okay, so to prove this claim, I want to use an equivalence of BQFs. So suppose we start with the BQF ABC, then that's going to be equivalent to the BQF A minus BC. And why is that? Well, you can just take the matrix giving the equivalence to be 1, 0, 0, minus 1. And then M transpose times A, B over 2, B over 2, C times M. You can easily check that's A minus B over 2, minus B over 2, C. Okay. So that's an equivalence of BQFs. And because D is invariant under equivalence, we have DABC equals DA minus BC. Okay. So what does that imply? Well, it implies that if we use we use this relation here, that implies that D0 of AC times b to the 0 plus D1 of AC times b to the 1 is congruent to D0 of AC times minus b to the 0 plus D1 AC times minus b to the 1. And then that implies that D1 of AC is congruent to its negative. Just by comparing the b to the 1 coefficients. So if D1 of AC is congruent to its negative, that implies that D1 of AC is congruent to 0, which means that b squared minus 4ac, this means that b squared minus 4ac divides D1 of AC. But how is that possible? I mean, D1 is a polynomial in A and C. There are no B's in there. That implies that D1 of AC must in fact equal 0. Okay, that proves the claim. So D1 of AC is 0, which means we can just ignore that term. Okay, next claim. Next claim, this is a bit harder. Your question?
I think it's just accidentally unmuted.
Okay. Next claim is about D1 of AC. Sorry, next claim is about D0 of AC. D0 of AC is an integer. Okay, let's prove this. Okay. For each integer k greater than or equal to 0, I'm going to let d1k of AC be the terms of degree k in the polynomial d1ac. Just the terms of degree k. So then d1 of AC is just the sum over all k greater than or equal to 0 of the degree k terms. We're just partitioning d1ac into polynomials, all of which have the same degree. Okay, sorry. Can't it be that 2d1 of AC equals 0 mod, but d1 of AC is not divisible? Well, I mean, so the thing to know here is that A, B, and C are variables. So they don't actually have any values. So if 2d1 of AC is equal to 0, mod b squared minus 4ac, then d1 of AC is equal to 0. Yeah. Okay, great. Okay, so yeah, so we've taken d1 of AC and we've partitioned it into these polynomials d1k, where each d1k is homogeneous of degree k. Okay. And then we just note that d1k of AC is necessarily invariant under equivalence for each k. The reason is that equivalence is a linear transformation. Oh, sorry, yes. I've put ones everywhere. Oh, goodness. I mean d naught. D naught k, sorry, d naught here. D naught. Thank you for finding these corrections. Okay, so yeah, so the thing to note is that d naught k AC is invariant under equivalence for each k. The reason is that equivalence is a linear transformation and it's not going to change degrees. So d naught k is invariant. And now let's take our integer k to be actually greater than 0. Sorry. K greater than 0. And we can write d naught k AC as a polynomial as follows. So this is going to be a sum from I equals 0 up to k of some coefficient hi times a to the I, c to the k minus I. Okay. Okay. So we expand out d naught k of AC like that. And now I want to use some equivalences. Okay, so the BQF ABC can be seen to be equivalent to CBA. And if you want to prove that, you can just use the matrix 0, 1, 1, 0 to relate them. So that implies that DABC equals DCBA. And then that implies that d naught KAC equals d naught KCA. Okay, so d naught K is symmetric in A and C. Okay. The next equivalence I want to use is ABC is actually equivalent to the following funny triple. A plus NB, oh no, getting a spam call. Sorry, A plus NB plus N squared C, B plus 2NC, and C. So that's a funny equivalence. And it is given by the matrix 1, N, 0, 1. You can do this for any integer n. Okay, so that equivalence implies that DABC equals DA plus NB plus N squared C b plus 2nc. Then that, of course, implies that d naught k of ac is congruent to d naught k of a plus nb plus n squared c comma c. Okay, so now I want to study these two polynomials here. So the thing to note about the polynomial on the left is that if you look at the coefficient of c to the k, well, what is the coefficient of c to the k? So if we look at the definition up here, c to the k corresponds to h0. So the coefficient of c to the k is h0. If we look on the right-hand side here, what's the coefficient of c to the k? The coefficient of c to the k, you can check the computation, is equal to d naught k of n squared 1. Okay. All right, so we have two polynomials that are congruent. On the left-hand side, the coefficient of c to the k is h naught. On the right-hand side, it's d naught k of n squared comma 1. Okay, so then the implication is that d naught k of n squared comma 1 is equal to h naught. And this is true for every integer n. This integer n that we chose here was anything, could be anything. And so we had this equality for every choice of the integer n. Well, what does that tell you? It tells you that d naught k is constant in the first variable. Okay. And then by symmetry, because d naught k is symmetric, we see that it's also constant in the second variable. Okay. Now, because d naught k is a polynomial of degree k, all of the terms here have degree k. The implication is that the hi's are 0 for every I. That is to say, d naught k actually has to be identically equal to 0. Okay, so what does that imply? Well, it implies that d naught of AC is the sum over k greater than or equal to 0 of d naught k AC. But what we proved is that when k is greater than 0, d naught k equals 0. So this is just equal to d00 AC. Now d00 is the degree 0 part, which means that it's just a number. That's an integer. So that proves the claim. Okay, the conclusion is that d of a, b, c is congruent to, well, let's see, how did I write this? Okay, yeah, so maybe what I'll do is I'll call this number d naught of AC, I'll call it m. Okay, so DABC is congruent to m modulo b squared minus 4ac. Sorry, congruent to m mod b squared minus 4ac. Okay, so what does that imply? Well, that implies that DABC is equal to m plus some polynomial EABC times b squared minus 4ac. Because then you could just set b squared minus 4ac equal to 0, if you set this equal to 0, then you'll get this congruence. Okay. Now DABC is invariant under equivalence. And the number m is obviously invariant under equivalence. And so is b squared minus 4ac. And so therefore, EABC must be invariant under equivalence. So EABC is a polynomial invariant under equivalence. And what's more, the degree of E is less than the degree of D. And then the theorem follows by downward induction on the degree. The point is that we just did some argument about, give some argument about D. Well, you can just run that argument on E and produce a polynomial of even smaller degree, F. And you can keep going like this until the degree hits 0. Okay, so that proves the theorem. Okay, so the discriminant is a unique polynomial invariant. Now you could ask the following question. So if the discriminant of F equals the discriminant of G, then is it true that F is equivalent to G? So we know that the converse is true. If F is equivalent to G, then the discriminants are equal. But the answer to this question is absolutely not. No. So as an example, you could take f of x comma y to be x squared minus 9y squared, and g of x comma y to be 3x squared minus 3y squared. And the discriminant of f equals 36, which is equal to the discriminant of g. But I claim that f and g are not equivalent to each other. And the reason is that 3 is not going to divide f prime for any f prime equivalent to f. Whereas 3 will divide g prime for any g prime equivalent to g. The reason is that you can just factor g as 3 times x squared minus y squared. And you can see that under equivalence, that multiplicative factor of 3 is going to stay the same. And so f and g cannot be equivalent. Okay. So forms of the same discriminant are not necessarily equivalent, which raises the question of given a discriminant, an integer, d, how many equivalence classes of BQFs are there of discriminant d? And regarding this question, we have the following second main theorem of the talk, which is that there are always finitely many equivalence classes, BQFs of discriminant d. Okay, so just as a note, in what follows, for the sake of simplicity, I'm just going to restrict consideration to BQFs of negative discriminant. That's just for the sake of simplicity. Everything I say will have an analog in the case of positive discriminant, but I'm going to get into that. Okay. All right, so the proof is what's known as reduction theory of binary quadratic forms. Okay, so for that, I need to make a definition. We say that a BQF ABC is reduced if 0 is less than or equal to B is less than or equal to the absolute value of A is less than or equal to the absolute value of C. So that's the notion of reduced. It's just some restraint on where the coefficients can lie. The claim is that there are finitely many reduced BQFs of discriminant D. Okay. Let's first prove that. So if it's reduced, then you can use these inequalities here to see that B squared has to be less than or equal to AC, which implies that D, the discriminant of B squared minus 4AC, is less than or equal to minus 3AC. Then that implies that AC is less than or equal to D over 3. Okay. Now, by assumption, we assume the discriminant was negative, so 0 is greater than D, and that's, of course, B squared minus 4AC. So that implies that AC is greater than 0. Okay. So we conclude that 0 is less than AC is less than or equal to D over 3. And that means that there are finitely many choices for A and C. Now, once A and C have been chosen, B is determined up to sign, by the equation D equals B squared minus 4AC. Because remember, D is fixed. And then we said that A and C had finitely many choices because they satisfied these bounds. And so A and C are determined up to finitely many choices. And once you've fixed A and C, B is determined up to psi by this equation. Okay. So that proves the claim that there are finitely many reduced BQFs of discriminant D. Isn't D over 3 negative, though? That's true. That sounds right. Wait, what? Oh, no. Did I make a mistake? Yeah, it's minus D over 3. Sorry. Minus D over 3. I missed a sign. I think that sorts it out. Yeah, thank you for catching that. Okay. So we've shown that there are finitely many reduced BQFs of discriminant D, but what we wanted to show was that there are finitely many equivalence classes of BQFs of discriminant D. And that will follow from the next claim, which is that every BQF is equivalent to a reduced BQF. If you just take this claim and combine it with the previous claim, you'll get the theorem. Okay, so let's prove the second claim here. So recall that we had this equivalence. ABC was equivalent to CBA. And to get that equivalence, you can use this matrix 0, 1, 1, 0. So we can always arrange for the absolute value of A to be less than the absolute value of C. And I'm going to denote this by move number 1. Okay. And the next thing I want you to recall is that we had an equivalence of the following form. So ABC, I'm going to sort of reflect an equivalence that I mentioned earlier. So this is going to be equivalent to A, B plus 2NA, and C plus NB plus N squared A. And this equivalence is achieved using the matrix 1, 0, and 1. Here, N can be any integer. Okay. Now, there exists a unique integer N such that B lies between minus the absolute value of A and the absolute value of A. Okay. So by choosing the integer N appropriately, we can always arrange for this, for B to lie in this range. Okay. So I'll call this move number 2. I see there's a question. Does your reduced polynomial have a good matrix analog? Well, not really. I mean, the matrix would be A, B over 2, B over 2C. And the reduced condition is just going to impose a condition on the sizes of these matrix entries. It doesn't really correspond to any particularly nice matrix. Okay, so I've defined 2 different moves so far. And now the third move is given by the following equivalence. ABC is equivalent to A minus BC. Okay, and that equivalence is achieved using the matrix minus 1, 0, 0, 1. And using this equivalence, we can arrange that B is greater than or equal to 0. Okay. So I'll call this move number 3. And now I want you to consider the following algorithm. So I'll sort of write in pseudocode. So while ax squared plus bxy plus cy squared is not reduced if the absolute value of A is greater than the absolute value of C, we apply step 1. Else, if B is less than or equal to minus the absolute value of A, or B is greater than the absolute value of A, we apply step 2. Else, if B is less than 0, we apply step 3. Okay. And then by induction, so that's the algorithm, by induction on the size, downward induction on the size of A, you can easily see that this algorithm terminates. So ax squared plus bxy plus cy squared will eventually be reduced after finitely many iterations of this algorithm. So that proves the claim that every BQF is equivalent to a reduced one. And then it then follows that there are finitely many equivalence classes of BQFs of a given discriminant. Okay, so I realize I'm already at 55 minutes, amazingly. Simon, I was wondering, do you think it might be acceptable to run overtime, or how much time could I run over?
That's fine.
Yeah, so there's actually quite a lot I wanted to say. Would it be okay if I ran maybe an hour overtime? How much do you think is reasonable?
Yeah, and so this class is 2 hours, and at some point I was planning on finishing my introduction to LaTeX. So it's not the end of the world if I can't do that, but it would be nice if I can.
Okay, maybe I'll try to omit some proofs, and hopefully it'll go faster.
Okay.
Okay. Thank you. Okay. So now I want to talk about the following question. So we've shown that there are finitely many equivalence classes of BQFs of a given discriminant. So the question I want to answer is, how are BQFs of discriminant D related to each other? Okay, so for this, I'm going to make a definition. Two BQFs of discriminant D are said to be concordant if they share the same XY coefficient. Okay. So then I have the following little result about concordant BQFs. So let F and G be BQFs where the discriminant of F is equal to the discriminant of G is equal to some D. And let M be some non-zero integer. Then there exist BQFs F tilde equivalent to F and G tilde equivalent to G, such that the first point is that the x squared coefficients of F tilde and G tilde are coprime to each other and also coprime to the number m that we chose. And the second point is that F tilde and G tilde are concordant, meaning that they have the same XY coefficient. Okay, so I think I can give the proof of this. It's not so bad. I'll omit some proofs later. The proof starts with the following lemma. There exists a BQF F prime, which I will denote by A1, B1, C1, such that F prime is equivalent to F and the GCD of A1 with M is equal to 1. Okay, so we're just focusing on the first BQF F here. We're going to arrange for an equivalent form F prime such that the GCD of A1 with M is equal to 1. Okay. So proof. So we can write F as A, B, C. Then if F prime is related to F by the matrix SUTV, then the x squared coefficient of F prime, that's equal to A1. And you can check that that's just F of S comma T. Okay. So if F prime is related to F by the matrix SUTV, then the leading coefficient A1 of F prime is just F of S comma T. Okay. So now suppose the lemma is false. You're going to go by contradiction. Then by the pigeonhole principle, there exists some prime p dividing the number m such that f of s comma t is congruent to 0 mod p. It's divisible by p for every choice of the pair s comma t. Okay. Now, the number of choices of the pair s comma t modulo p is at least 3. For example, you could choose s comma t to be 1 comma 0 or 0 comma 1 or 1 comma 1 and so on. Okay. So thus, f of s comma t has at least 3 distinct roots. Modulo p, which is impossible because the degree of f is 2. Oh no, there's a problem. Okay. So this isn't quite true because if all the coefficients of f are divisible by p, then it'll be congruent to 0. Okay, so what I should do is, I made a restriction earlier. I said in what follows, we're going to restrict to BQFs of negative discriminant. I'm also going to restrict, we'll also restrict to BQFs where the GCD of the coefficients is 1. Okay, that'll avoid this problem. Okay. So yeah, so now what we're saying is we have this BQ of F. It's got at least 3 distinct roots modulo P. And that can't happen because the degree of F is 2. Okay. Okay, so that's the first lemma. So this lemma establishes that we can find this equivalent form F prime equivalent to F, where the GCD of the first coefficient of F prime with M is equal to 1. Okay. The next lemma. Okay. Next lemma states that there exists a BQF G prime, which I'll denote by A2, B2, C2, such that G prime is equivalent to G, and the GCD of A2 with A1 times M is equal to 1. And the proof of this lemma is exactly the same as the proof of the previous lemma, so I'll omit it. Why can't we just restrict? Doesn't this hurt the generality? Yes, it hurts the generality. But what should I say? I guess we're generally not interested in forms where the GCD is divisible, where the GCD of the coefficients is divisible by some prime. Yeah, people are typically not interested in those BQFs as much. The reason that you're not interested in such BQFs is that, so suppose you have a BQF, this is an aside, so you have a BQF ax squared plus bxy plus cy squared, where the GCD of ABC is equal to some number m, say. Then you can look at this, you can just divide by the GCD, a over m x squared plus b over m xy plus c over m y squared. So that's a new BQF with integer coefficients. And if we understand which numbers this new BQF represents, then the old BQF represents just m times those numbers. So sort of understanding the ones where the GCD is 1 is enough in some sense. Okay. So that was all just an aside about why we can restrict to these BQFs where the GCD is 1. Okay. So yeah, so we constructed using these lemmas BQFs G prime and F prime equivalent to G and F, satisfying some coprimality conditions. Okay, so now I have another little lemma, which is that B1 minus B2 is congruent to 0 mod 2. So remember, B2 was the XY coefficient of G prime, and B1 was the XY coefficient of F prime. And I'm saying that their difference is even. Okay. So the proof, well, B1 squared is equal to 4a1c1 plus d. And that's congruent mod 2 to 4a2c2 plus d, which is equal to b2 squared. So that proves that B1 minus B2 is congruent to 0 mod 2. Okay. So now let's complete the proof of the proposition. So now, by Bézou's lemma, since the GCD of A1 and A2 is equal to 1. So remember, we arranged that the GCD of A1 and A2 is equal to 1 in the second lemma. Since the GCD is 1, there exist n1 and n2 integers by Bézou's lemma, such that B1 minus B2 is equal to minus 2n1a1 plus 2n2a2. So the reason that we can put 2's in here is by the third lemma, which said that B1 minus B2 had a common factor of 2. Okay, so that's Bézou. And then you can rewrite that. That says B1 plus 2n1a1 is equal to B2 plus 2n2a2. But now recall that if you had A1, B1, C1, well, that was equivalent to a BQF of the form A1, B1 plus 2n1a1 followed by something. And that equivalence happened by means of the matrix 1, 0, and 1, 1. And also recall, similarly, that A2, B2, C2 was equivalent to A2, B2 plus 2n2a2, and so on, where the equivalence happened by this matrix 1, 0, n2, 1. Okay, but now B1 plus 2n1a1 equals B2 plus 2n2a2. So the XY coefficients are the same. And that completes the proof of the proposition. So why does that finish the proof of the proposition? Well, we've arranged for the XY coefficients to be the same. So if we go up to the proposition, that verifies that the two new forms are concordant to each other. And we wanted also that the x squared coefficients are coprime to each other and coprime to m. Well, we arranged for that using the first two lemmas. The GCD of A1 and M is 1, and the GCD of A2 and A1M is also equal to 1. So that verifies the first part of the proposition. Okay. So the point is that if you have two equivalent BQFs, then you can arrange to you can find equivalent BQFs. Sorry, I'm misstating this. Yeah, so sorry, if you have two BQFs, F and G of the same discriminant, then you can replace F and G with equivalent BQFs F tilde and G tilde such that their XY coefficients are the same. That means that they're concordant. And then you can also arrange for some additional properties to be satisfied. Okay. Okay. So now I want to make a definition. So let F and G be BQFs, where the discriminant of F is equal to the discriminant of G is equal to some D. And choose a BQF F tilde equal to A1B C1, G tilde equal to A2B C2, such that F tilde is equivalent to F and G tilde is equivalent to G, and also such that 4A1 A2 divides B squared minus D. Okay, so these first two conditions are mild. I mean, you're just choosing equivalent ones. And remember that, and note that F tilde and G tilde have the same XY coefficient. So we're choosing them to be concordant, and we can do that by the previous proposition. But this third condition is quite strange. How can we arrange for B squared minus D to be divisible by 4A1 A2? Well, note that if the GCD of A1 and A2 is equal to 1, and remember by the proposition, we could arrange for the GCD to be 1, then 4A1C1 and 4A2C2 both divide B squared minus D. But because the GCD of A1 and A2 is 1, that implies that 4A1A2 divides B squared minus D. So even though this condition that 4A1A2 divides B squared minus D looks funny, we can always arrange for that to be true by the previous proposition. That is, we can choose F tilde and G tilde so that that condition is true. So given that choice of F tilde and G tilde, we can define the composition of F and G, which we denote by F dot G. The composition of F and G is the following BQF. So F dot G of XY is equal to A1, A2, X squared plus BXY plus B squared minus D over 4A1, A2 times Y squared. So this is how two BQFs of the same discriminant are related to each other. If you take F and G of the same discriminant, you can produce F dot G. Okay. And now there are some very beautiful theorems about composition that I'm not going to get a chance to prove, but I'll just state them, and you can try to prove them using equivalences yourself. The theorem is that the definition of composition is well defined. So F dot G does not depend, or I should say, I should rewrite this as follows. So the equivalence class of f dot g does not depend on the choice of f tilde and g tilde. Because if you look at this definition of f dot g over here, we're choosing f tilde and g tilde, and then we're using that f tilde and g tilde to make f dot g. And so it's important to understand whether the definition of f dot g really depends on the choice, and it doesn't. Okay, so that's a theorem. I'll leave the proof as an exercise. I noticed there was some discussion in the Discord about how that's a bad thing to do, but oh well. Okay, and I'll also leave another result as an exercise. Corollary, the set of equivalence classes of BQFs of discriminant D is a finite abelian group with respect to the operation of composition. So this will be comprehensible to those of you who know some group theory. I'm going to leave the proof as an exercise, but I can outline for you what the steps will be. The first step is to prove the abelianness, the commutativity. So you want to show that f dot g is equivalent to g dot f. Second step would be associativity. F dot g dot h should be f dot g dot h. And the third step is identity. So there has to exist a BQF E such that E dot F is equivalent to F for every F. The same E has to work for every F. Okay. And for every F, the last property is inverses. There should exist an F inverse such that F inverse dot F is equal to this identity element. So once you've verified those four things, none of which are hard, you can complete the proof. Okay, all right. So that's composition, and I want to conclude the talk, which I should be able to do in I think 10 minutes or so, using by talking about a Diophantine application of composition. Now I want to talk about a Diophantine application. So this is getting to more of my research. Okay. So for this, I'm going to make a definition. So given an equation, z to the n equals f of x comma y, where n is a positive integer, and f of x comma y is a homogeneous polynomial with integer coefficients. We say that a triple of integers x naught, y naught, z naught is a solution to the equation z to the n equals f of xy if z naught to the n equals f of x naught, y naught, and the GCD of x naught and y naught equals 1. Okay. So the question that is a key subject of my research is How often do equations of the form z to the n equals f of x, y have or fail to have a solution? Okay. And now I want to give you a theorem concerning the case where the degree of f is 2, the case of BQFs, which we've been talking about. So let f be a BQF, then z to the n equals f of x, y has a solution if and only if f is equal to the n-fold composition, so the composition n times with itself of a BQFG. So the condition for the equation z to the n equals f of x, y to have a solution, that condition can be expressed in terms of composition of BQFs. And the condition is just that if you take f, it should be expressible as the n-fold composition of a BQFG. Okay. And so I should say who this theorem is attributed to. I think it's attributed to Castles. 5 years ago, when I first started talking to my advisor, Manjul Bhargava, we thought we proved this theorem, and we were very excited. But as often happens in research, you realize that somebody else proved it before. Okay. So the proof starts with a claim, which is that the equation z to the n equals f of x, y has a solution if and only if f is equivalent to some h for some BQF h whose x squared coefficient is an nth power. Okay, let's prove this. So this is an if and only if, so I'll prove the forward direction first. So take a solution, x naught, y naught, z naught to our equation. And since the GCD of x naught, y naught equals 1, there exist integers n1 and n2 such that n1 x naught minus n2 y naught equals 1. Then transforming so we transform f of x, y into the following BQF, f of x naught x plus n2y, comma, y naught x plus n1y. If you do that transformation and you expand out what you get, then you'll get z naught to the n times x squared plus some other terms. So if you have a solution, then you can do this transformation right here to get a BQF whose x squared coefficient is an nth power. Now, for the reverse direction, if f of x comma y were equal to an nth power times x squared plus other terms, then the triple 1, 0, a is a solution. So that proves the claim. Now, For the next claim, is that f is equivalent to h for some BQF h whose x squared coefficient is an nth power if and only if f is equal to, or f is equivalent to, f is equivalent to an n-fold composition. Okay. So if you combine this claim with this claim, then you'll get the theorem of Castle's. Okay. So let's prove that. This is a bit of a more difficult claim. So for the forward direction, let's write h as a to the n b c. Then you can check that h is equal to a to the n minus 1c composed with itself n times. Okay. So for example, when n equals 2, you take a, b, a, c, and compose it with itself. Well, what is the criteria? What are the criteria for composition? Well, first of all, the forms have to be concordant, and their x, y coefficients are the same. So that's good. And then under some other conditions, this would be equivalent to a squared b d minus b squared over 4a squared. And the other conditions are precisely that this number here has to be an integer. But the discriminant here is equal to b squared minus 4a squared c. So sorry, this is d. D is b squared minus 4a squared c, and that implies that a squared or 4a squared actually divides d minus b squared. So that verifies this condition here. And so at least when n equals 2, we see how the composition works, and the same argument will work for any n. Okay. Okay, so that's the forward direction. Now for the reverse direction. So we write G as ABC. So as before, we can assume that the GCD of A and D is equal to 1. Remember, we had a proposition that said that you could always arrange for the first coefficient to be coprime to any number you want. Well, we are arranging it now to be coprime to the discriminant. Then the GCD of A and B has to be 1, because if A and B had a common factor, that would divide the discriminant. So there exists some integer n such that nb is congruent to any number we want modulo a, and so we can make it congruent to minus c. That follows because b is coprime to a. And then ABC is equivalent by the equivalence that we mentioned before to AB plus 2NA C plus NB plus N squared A. And now C plus NB is 0 mod A, and N squared A is 0 mod A. So this third coefficient is just congruent to 0 mod A. Okay. So then this is just equal to a b plus 2na ac prime for some integer c prime. Okay, and now we can compose. So a b plus 2na and ac prime composed with itself. Well, the question is, can we compose it with itself? The forms have to be concordant, and they are. And then the discriminants have to work out. So, or sorry, the third coefficient has to work out. So this composition is equivalent to a squared b plus 2na and d minus b plus 2na squared over 4a squared. Okay, so the thing that we need to verify is that this third quantity is an integer. So we compute the discriminant again. The discriminant is b plus 2na squared minus 4a squared c prime. And so that implies what we need, that third coefficient is an integer. Okay. So what does this prove? Well, this proves that if you take a form G and you sort of compose it with itself, then you'll get a form whose first coefficient is a square. And just by doing this inductively, you'll see that composing G with itself n times will give you a form whose first coefficient is an nth power. Okay, and that proves the claim. And it also finishes the proof of the theorem. Okay, so going back to the theorem statement of Castle's, this equation here, z to the n equals f of xy, has a solution if and only if f is an n-fold composition. And I just want to very briefly finish by mentioning the results of my own from my thesis. So this result was partially proven by Bhargava in 2013 and also partially proven by me in 2019. Okay. So fix a number m at least 3, then most, I should say an integer m at least 3, then most equations of the form z squared equals f of x comma y, where f is a homogeneous polynomial with integer coefficients of degree m, have no solutions. Most of these equations have no solutions. So how do we prove this kind of theorem? Well, we actually use a very similar strategy. Okay. So we create a space with a composition law. Create a space with a composition law on it. For example, the space of BQFs. And we show that a solution gives rise to a twofold composition. So remember, Castles showed that if you had a solution to z to the n equals a BQF, then you get an n-fold composition. Well, what we show is that if you have a solution to this equation, c squared equals f of x comma y, where f is some polynomial of degree m, then you get a twofold composition. And then we prove that such twofold compositions are very rare. Such twofold compositions don't happen very often. And so most of these equations have no solutions. Okay. So yeah, that concludes my talk. I'm very, very sorry for running over time. Thank you for your patience and for listening.
Hey, thank you. So, does anyone have any questions?
I'm also hooked up to the Discord, so if you have any questions, please feel free to ask me at any time.
Okay, so there's a
How do I define rare?
Yeah.
Oh yeah. So as the degree m tends to infinity, I would say, the percentage of insoluble equations tends to 100%. And in fact, the proportion of insoluble equations is 1 minus little o of 2 to the minus m over 2. So what this means is that the proportion tends to 100% exponentially fast.
Yeah, any other questions?
Yeah, I noticed that people are asking for the PDF in the Discord. I'll try to figure out how to do that.
Yeah, well, okay. So thank you for a great talk. And as that concludes that part of it,